Then basically every time you're making a call, these sensors are analyzing your breath. And in your breath, you have very small traces of certain molecules that are an indication of some diseases being developed in your body. So I could imagine that Apple then gives you a notification, you need to go to your doctor because we see some abnormality in your breath.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE Company Database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below. And now, let's get on to the episode. Hey everyone, today's special guest is Aaike van Vugt, the CEO of VSParticle and a Forbes 30 under 30 honoree in Europe. VSParticle specializes in selling equipment that provides its research and industry customers with the tools to manufacture nanoparticles and nanostructured materials. The company is currently developing a 3D nanoprinter, which can act as the building block for nanotechnology applications in a variety of applications like sensor technology, LEDs, electronics, and more. So Aaike built this business from the ground up after co-founding the company the day after he graduated in 2014. And since then, he's won many startup competitions and awards while building VSParticle into what it is today. So I'm super excited about this technology and learning more about your experiences. So we appreciate you joining us today.
Thanks for having me. I'm very happy that you are putting so much time in this podcast and that there are people really caring about the development of new materials. So I'm very happy to participate and share my knowledge that I've gained in this field in the last 7 years already.
Yeah, thank you so much. That means a lot. We're excited to have you. So before we get into the technical aspect of it and the nanoprinting and your core technologies, could you maybe talk through your motivation to start VSParticle and what the journey of starting a company was like coming straight out of college?
Yeah, definitely. I think that's a very good question. So there are two sides to these questions. One side is more personal interest, and the other side is more the value it could bring to society. So coming from college, I think we have learned a lot. So you have learned some basic, just to adapt yourself to a new field and get acquainted with it and find your way through it. But then you go into the business. So producing revenue, building companies, growing teams, all these other aspects that you are not really trained that much during college. So I always had the interest that if you would be, let's say, starting a new company, there were so many aspects that you could still learn. So it's more like an extension of my already, I would say, academia work, but then focusing on other aspects than you would be trained in just from college. So that was my personal interest, to get hands-on experience in some of the other fields. On the other side, while I was getting in contact with the technology that was originally developed at the University of Delft and is now brought into the company to be introduced into the market, I realized that if you look back into history and our capabilities as humankind to process materials, and then I'm especially focusing on inorganic materials, so metals and semiconductor materials that we are extracting from this Earth's crust, then there is so much value gained by becoming better in, let's say, processing those materials into new applications, into new form factors, into new markets, that if you are able to contribute in a positive manner to the future of these developments, then it's a huge opportunity to add something to the future of the development of the human species, from my perspective. So that was more the aspiration of what can we bring to the, let's say, the macroscopic evolution process. And also the personal part was more about learning hands-on all the other fields that I haven't seen during my college.
Right. And that's super inspiring. I guess I was just wondering then, since the undergraduate program, from my experience, is very broad in nature, but you almost have to get some experience or pursue an advanced degree to go really in depth. How did you balance that with, I guess, starting a company where you kind of need to have some technical depth and you need to also have that business background? How did you learn the requisite skills and gain that knowledge base?
So I think bit by just being naive. I think that is part of who I am. It's very helpful to just get started. And then along the way, you realize all the things you should have known from the start, but then, yeah, you're already in the process, and then you will adapt to it, and you will make sure it happens. What really helped me is that I didn't start the company by myself. So in the beginning, we were 3 of us. So it was the original professor at the University of Delft, Professor Andreas Schmidholt, who worked his whole scientific career on new methods to build up or break up bulk materials into very small nanoparticles, and then find the most flexible and most well-controlled process. And our CTO, Tobias Pfeiffer, who did his PhD on this core technology. So I was really happy that he joined, because then he would take care of most of the real deep tech technology, and he is very good in that. And then I could, let's say, get basic understandings of what we are able to do and how the technology works, but then could focus more on how to extrapolate this towards the commercial side and industrial customers and academia.
That's super fascinating. Awesome. And I know in a previous conversation when you and I had a call, you mentioned that one thing that inhibits the rate at which researchers can kind of push those boundaries of materials innovations is it revolves around the lack of standardization, and that kind of leads to longer trial periods to try and replicate what's already been done instead of stacking and building upon each other's work. So how does your vision for VSParticle play into addressing this issue?
This is, I think, a very, very important question. And this is, I think, the fundamental problem that we are trying to solve at VSParticle. And I think we are quite successful in it so far. So let me first maybe talk a bit about the type of materials we are focusing on. So we are more and more trying to call it the 4th wave of innovation in the advanced material space. So the first one was really our ability to extract the bulk materials. So extract pure gold, pure silver, pure copper, and then constructing the periodic table. The second one was, we started to mix those materials together to form alloys. That's when we were able to develop stainless steel, which was a huge innovation back in the days that enabled all kinds of new products and applications. The third wave was when we were able to become better in manipulating matter at the nanoscale. So we were able to make transistors smaller and smaller. We are still in this path. So we have PVD, CVD type of technologies in combination with lithography. So it's a subtractive process to make computer chips more powerful. And that's the whole Moore's law development. But the materials used by the semicon industry, so by the industry that is producing most of the chips, they are staying away from what we call quantum enhanced materials. So they want to have the smallest materials that still exhibit bulk properties. Because if you go below, let's say 5 nanometer in size, so you could really go to the smallest scale, then you will get the appearance of drastic change in material properties due to quantum mechanics, the physical laws at the nanoscale. But you can imagine that if you have huge change in material properties, depending on your size, that if you have some variation in your process, that could have huge impact on the performance of the final product. So chip manufacturers, they don't like it. They want to have a very reproducible, very controlled process. So they stick to bulk properties, which is understandable. But we see it not as a problem. We see it as an opportunity. So we think to progress our ability as humankind to, let's say, shape new materials and to develop the applications of the future, we really need to start mastering this unexplored field of quantum enhanced properties. So we need to embrace it, and we need to develop technologies and processes to really unlock all that is possible by manipulating matter at that very small scale. This is also an attempt that is not only done by us, but if you look into research, especially into the use of nanoparticles, and especially nanoparticles sub 10 nanometer in scale, you see a tremendous growth of scientific publications since the beginning of this millennial. The microscopes became better, so we can now see the nanoparticles. We can study them in situ while they are exposed to all kinds of environments. But still, making those nanoparticles is closer to being an art than being a very sophisticated, reproducible engineering practice. So on average, to synthesize a new nanoparticle, which has these quantum enhanced properties, could take up weeks, even months of complicated chemistry. And then we don't know what the properties are of all those nanoparticles. So it's a trial and based development. So we need to synthesize hundreds, maybe thousands of different nanoparticles before we found one that really has the properties that we were looking for to boost our battery or solar cell or a sensor. And if you know that every cycle takes up a couple of weeks to months, and you need to do hundreds, maybe thousands of those cycles, you are stuck in a 15-year development process. And then I didn't even start about the complexity of scaling the production of those materials up to high volume production. So it's a very tedious, complicated, costly process to develop a new material from the first experiment all the way to high volume production. Even though I just explained to you that our ability to bring those new materials to the market is essential for the evolution or innovation in many different fields. So what we are trying to do is to solve some of the fundamental problems that make these development cycles take weeks or months and bring them down to days or maybe in the future even minutes. And two aspects are very important, is reproducibility. So if you make a sample today and you want to make a sample next week, or you make a sample in Europe and you want to make the same sample in the US, that it works. So you get exactly the same sample. So we have a standardized production process. And the other one is speed. So it needs to be fast. It doesn't need to take a couple of days or weeks or months to synthesize that specific nanoparticle. You need to design a nanoparticle basically on your computer, press enter, and then it needs to come out of the production tool in the matter of hours, and then you need to be able to analyze them. And these two aspects, so speed and reproducibility, and the other one is versatility, because there are a huge amount of nanoparticles that you want to investigate, what we are doing. If you are able to introduce those three into, let's say, the new standard of nanoparticle processing, then you are fundamentally able to change the whole ecosystem, because then a researcher in Canada can work on top of the work done by a researcher in Europe. And this is something that is currently very, very difficult. Researchers are trying to replicate work of each other, but yeah, it's all, as I mentioned, more like an art. So it's very difficult to reproduce a material. Even for a researcher to reproduce his own results is very difficult. And that's a fundamental shift we want to bring into the field, because then the whole field becomes to accelerate, and then we can lead humanity into this next age where we are unlocking huge amounts of capabilities through these quantum enhanced properties.
Yeah, absolutely. You can innovate at a more rapid rate when everybody's building on each other instead of working in parallel with each other, right?
Correct. And our philosophy is not to do everything in-house. So that's another, we could keep the technology to ourselves and then try to unlock this new paradigm by ourselves. But we believe more in the community approach. So we want to set the new standard that enables the whole, I would say, global effort, all the people and all the brilliant scientists that are pushing this field forward to move faster and to build on top of each other's work. And I think that's very important.
I love that. So then can we go into exactly how this nanoprinting technology works? Like you mentioned the variation that current manufacturers aren't a fan of. And so how do your nanoprinters, how will they be able to generate nanoparticles in a controlled manner? And are there any challenges in terms of like the complexity that comes with this that you're facing? How are you overcoming all of that?
Yeah, so it's maybe good to explain that most nanoparticles are synthesized through wet chemistry. So chemistry came up quite early in the 60s, 70s, and it was a very powerful technology. And you are able to synthesize inorganic nanoparticles in a liquid solution through chemistry. So you can mix in a combination of different metal salts. You are able to reduce them, and then you go from a metal ion to a metal atom. And then those atoms are colliding into each other into the liquid solution and then forming bigger and bigger nanoparticles. And this is a very easy, or it looks to be a very easy process. So you just buy some glassware, you buy some chemicals, some stirring and heating equipment, and then you can start off in your chemistry lab and synthesize all kinds of materials. But chemistry is a very powerful technology, but not in the case you want to make well-controlled, very small inorganic nanoparticles, because there are so many parameters that you need to control in this chemistry process: the pH, the amount of chemicals, the stirring speed, the temperature. To prevent agglomeration and further growth, you need to add new chemicals, reagents or surfactants that are, let's say, separating the nanoparticles from each other and preventing additional steps. So to optimize all those different parameters, and we call that a production recipe. To optimize this recipe, you are losing a lot of work, because for every new nanoparticle, even a slightly change in the particle size, you need to develop a whole new recipe by varying all those different parameters. So it's very slow because you need to develop a new recipe for every new nanoparticle. It is not so reproducible. That's a fundamental problem to chemistry because there are so many parameters, you can't control all of them exactly the same time, the second batch. And the other one is then you end up with nanoparticles being stabilized in a liquid solution. But that's not your final product. That's not your solar cell. That's not your battery. So in the end, you need to get them out of the liquid solution and immobilized onto an electrode of a battery or on top of a solar cell or on top of a MEMS device for sensors. And the way that is done is just pouring them over from the liquid solution, putting that into the oven and evaporating all the chemicals out of it. And that's a very complicated process because the moment you are heating up the substrate to evaporate the chemicals, you're also agglomerating, sintering, contaminating the nanoparticles. And then, you don't have the nanoparticles in your final product. They are not the same as the nanoparticles you synthesize in your liquid solution. So even though it feels like you're almost there, you have your nanoparticles in your liquid solution, you have your substrate, it's almost mission impossible to get them without being changed, immobilized on your support. So both chemistry is part of the problem, but also the fact that you need to do post-processing to get the particles onto your final product. And in our nanoprinter, it's a full end-to-end solution. So in a few milliseconds, we make the nanoparticles through a physics process. So it's evaporation condensation. So we form electrical sparks to evaporate the source material. So for example, we have two solid rods of gold. In between those rods, we form electrical sparks. We evaporate gold atoms. And out of this evaporated cloud of gold atoms, we form very small, pure gold nanoparticles in a gas phase. So it's a gas phase. It's not chemistry. There's no liquids. Those nanoparticles that are growing are then being transported by carrier gas. It could be argon or nitrogen to keep them controlled or to keep the environment controlled. They are transported to our printing stage, which is in the same product. They are directly printed in an additive manufacturing process into your final product. So it's not only about synthesizing nanoparticles, it's also about directly post-processing them in the right manner and getting them on the right place in the right structure of your final product.
Is that method appropriate for like metals and semiconducting materials only, or is it applicable to material classes beyond that?
Again, we need those electrical sparks to happen. So the material needs to have sufficient conductivity. We can post-process the material. So we can introduce oxygen, for example, in the gas stream to oxidize, so to make oxides or ceramic type of materials. But we always need to start with, for example, conductive copper. If you look into the periodic table, our process, so the beauty of our nanoprinter is that it's material agnostic. And why is it material agnostic? Because in these electrical sparks, the temperature goes up to more than 20,000 degrees Celsius. And there's almost no material that is not evaporating at these high temperatures. So for our process, it doesn't really matter if you put in gold or you put in silver, both will evaporate and both will start this growth process of nanoparticles in the gas phase. So we can process almost 2/3 of the periodic table, which is a huge amount of materials. We can mix those materials in any combination in a nanoparticle. So we can also mix different materials in a nanoparticle. We can mix nanoparticles of different materials to form, let's say, a sort of compound. We can make alloyed nanoparticles. So we can mix almost anything with anything. So 2/3 of the periodic table, you can make any combination. So then already you have an option space that is huge, enormous. And then in our process, we can control the growth of these nanoparticles. So we can both control the elemental composition of the nanoparticles, but also the shape and the size. And those two factors are most dominant factors in controlling their quantum enhanced properties. But just to be clear, we don't do anything with organics. If you put an organic molecule in our system, it will be burned because it doesn't withstand these huge or these very high temperatures.
Right. So then I think maybe another good way of talking about this is comparing your nanoprinting technique to atomic layer deposition, or ALD. So how is your process different from ALD, and what are the benefits of using a nanoprinter relative to ALD?
Yeah, it's a very good question. First of all, let me say that ALD is a beautiful technology. I think it's a marvel that we are able to develop it, and it's very powerful. But I already talked about these 4 waves. First is discovery of the different materials. Second is combining them into alloys. Third is about micro nanostructuring. And that's really where ALD plays a very important role. Because if you combine it, especially with lithography, exposing different patterns onto your layer and then etching them away, you are really able to make very controlled layer thicknesses with ALD. And then it really is a powerful tool to produce those computer chips. With ALD, you are also able to make, because you are building new materials layer by layer, so it's really a 2D type of material, you're able to control them, the thickness of the layer, very, very precise. You can even make layers of different atoms stacked on top of each other, so gold atoms and then another material and then another material. So in that sense, you're also able, if you make those layers very thin, you're also able to unlock quantum enhanced properties. But it's all still a two-dimensional layer, a two-dimensional sheet. So the option space that you have to create quantum enhanced properties is substantially, but is not as humongous as you have if you build up materials but with three-dimensional structures. So what we do is we don't build up a material layer by layer. No, we first build these nanoparticles as, let's say, Lego building blocks, and then we stack them on top of each other to form a new layer. Most of the layers that we are printing are still, you could consider them, let's say, 2.5D or 2D, but the morphology of the layer is completely different. We don't build them up atomic layer by atomic layer. We build them up by stacking those nanoparticles. And because we stack them up by nanoparticles, we have additional, I would say, knobs to turn to even unlock more, almost 2 or 3 orders of magnitude more quantum enhanced properties. Because we can play with the elemental composition of those nanoparticles and their size, and both of them have huge impact on their properties.
So with these conductive materials, I was just wondering, are there any challenges when, so you're stacking it nanoparticle by nanoparticle rather than like layer by layer? Are there any challenges in that stacking mechanism to make sure that it's aligned exactly how you want it, that there's no misalignment or anything like that?
Yeah, so there's one difference. So putting down layers, either with PVD or ALD, and then applying lithography to make transistors or to make very fine patterns used for computer chips is a very accurate and relatively well-controlled process. But again, they are using materials that are also well-controlled because most of them are, let's say, somewhat bulk, behaving similar to bulk properties. It's really a fundamental paradigm shift. There's so much still to be explored regarding those quantum enhanced properties. How do we keep them stable? How do we control it in a sufficient way that every sample that we print is exactly showing the same quantum enhanced properties? It's a new technological challenge. But if you are able to master it, then the possibilities are endless. It's both a big challenge, but it's also the biggest possibility that we can unlock at this moment if you look into the next phases of new materials. It's not that our materials are used with lithography, for example. So our materials, I don't see them being used for the production of computer chips because our materials are unique because they have these quantum enhanced properties. While the computer chips, they don't want quantum enhanced properties. They just want, let's say, very reproducible bulk properties, but then in a very small, precise manner to make the most transistors per square centimeter to make the most powerful computer.
Yeah, absolutely. So then let's get into some applications that this nanoprinting technology is good for. And so we've now explored the fundamental aspects of the technology. So your website mentioned that MOX or metal oxide sensors are a good application for nanoprinting. Could you explain what are common uses of these sensors, why they're important? Just give some background and the benefits of applying nanoprinter technology to produce these sensors relative to what's currently used.
Yeah, maybe before I dive into metal oxide gas sensors, it's good to mention that if you are introducing a brand new, I would say, field of new materials that is unexplored, the first thing that you only can do is trying to find those applications where the materials that we are introducing can directly be applied. And maybe they are not the most groundbreaking, but it enables us to scale the technology and to enable mass manufacturing and then become established in different industries and then grow from that point on forward. So that's what we have been doing in the last 5 years while we are developing while we have been developing the nanoprinter, is to really do a whole bunch of different validation studies to investigate different markets, which enables us to condense, let's say, an application roadmap where we see, okay, what are the first applications we can introduce to the technology in and how will that progress over? On the other side, due to COVID, we have seen a massive awareness growth among customers about indoor climate systems. So we suddenly became aware about very small droplets that we are exhaling, or when you are sneezing, or when we are talking, that are existing in the gas environment around us. So that's why we have these regulations that schools need to open up windows to have sufficient ventilation, et cetera, et cetera. But this is all primarily targeted towards COVID or towards this virus. But there are many more chemicals flying around in our homes. So if you buy a new piece of furniture, there are all kinds of chemicals still coming out of your furniture that are potentially toxic for us, that are growing in concentration, if you are not having sufficient ventilation in your system. And we know also all the smog-related problems in some of the big cities around the globe, where you also have very polluting industries. So people really become aware about this and more concerned. So people are looking for new technologies to get more insight. And to give them those insights, gas sensors are very important. And there are a variety of different types of sensors. I will not dive deep into that, but one of them, metal oxide GAM sensors, is a very powerful, miniaturized, cheap type of sensor that has the potential to be deployed in all type of consumer electronics. From my perspective, I think the most powerful future, I would say, outlook would be is if we can get those sensors small enough, but also consume less enough energy so that they can be integrated into your mobile phone. And then basically every time you're making a call, these sensors are analyzing your breath. And in your breath, you have very small traces of certain molecules that are an indication of some diseases being developed in your body. So I could imagine that Apple then gives you a notification, you need to go to your doctor because we see some abnormality in your breath. But we are not there. We are currently in the phase of developing CO2 sensors to measure the concentration of carbon dioxide in your office or in your home. So that gives you an indication you need to open up a window to get more oxygen in, or some other basic compounds. The specific type of materials that our nanoprinter is making, these nanostructured materials built up out of nanoparticles, are very powerful to boost the performance of those sensors. So we print them on MEMS devices, and we can tailor their properties to be very active on molecule A or molecule B, or maybe we can print an array and then we can analyze almost any molecule that you're looking for. So it's a specific example of an application that already exists, that was already using nanoparticles, where our technology, because of the speed and the standardization or the reproducibility that we bring and the quick path toward high volume production, just accelerates this application towards the future that I described.
Yeah, that was fascinating. I didn't even think about that. I was like eyeing my couch over here and I was like, but so you mentioned, I guess, the factor of being cheap as well, so that it can be in like households everywhere, or maybe even in your phone and things like that.
Or in your fridge or whatever application you can think.
Right. And so how does that factor into play with nanotechnology? I know that generally, cost of manufacturing, cost of scaling can be a challenge. So I was just wondering, how does that come into play for household cheap sensors?
The beauty about these sensors is that you only need, let's say, a nanogram of material to provide the MEMS chip with its sensitivity. That producing a nanogram of these nanoparticle-based materials is relatively straightforward with our nanoprinter, because again, it's an all end-to-end solution. We don't use chemicals, we don't have any waste we need to think about. We just use electricity. We use it to form the electrical spark. So on a sunny day, the electricity price is very low. That really helps us bringing down the cost to process the materials and to enable these next generation sensors. Also on the sustainability part, it really fits in. It's only using electricity and a carrier gas, and there's almost no waste. And it's a pure, well-controlled conversion of bulk materials into, let's say, your ideal nanoparticle that you can use as a building block to build up new materials.
Yeah. Okay. I was just about to ask about the sustainability aspect, because it's been really refreshing to see, like, the guests we have on our episodes really emphasizing sustainability. And so VSParticle provides another unique way of moving towards a greener future. And so we wanted to touch on that, which it involves electrocatalysis and heterocatalysis, as decarbonizing our energy and fuel sectors is very important to a sustainable future. So can you talk through how nanoprinting in particular can aid in this transition?
Again, coming back to the third wave that I described. So our ability to make micro nanostructures, make those transistors smaller and make those computer chips more powerful. But in the end, it's flipping bits. It's going from ones to zeros, doing calculations and then processing all the data and enabling applications like your smartphone, your laptop, and let's say cryptocurrency or whatever, Web3 or whatever digital innovation that we are seeing these days, or AI. Sensors are analyzing machine learning algorithms, but it's all based on flipping bits. But I think what is very important for the coming decades is to move from just flipping bits to flipping atoms. So what we need is a new ability to unlock those quantum enhanced properties that give us power to still consume electricity, but consume it to move molecules. So to split water into hydrogen and oxygen, or to be able to reuse carbon dioxide through CO2 electrolysis and to make it into a jet fuel. So, and that's really a field where we see that those quantum enhanced properties are, or nanoparticle based materials are very crucial. So it's a completely new field that is coming up. Again, a field that is very slow due to lack of reproducibility and lack of speed, but also lack of global orchestration from my perspective. As you said, we are selling tools. So we are, let's say, supplying both academia, institutes, and corporate R&Ds, but also in the end, going for mass manufacturing tools to a variety of customers. And we see many customers trying to exactly examine the same nanoparticle. And from my perspective, it's a bit of a pity that we are in this global crisis. We know that the development of those new materials is a cornerstone solution to many of those problems, especially the industries that are difficult to decarbonize. And we are wasting our time just to compete with each other instead of, let's say, orchestrating and say, okay, I will analyze these materials, you will analyze these materials, and then next month we will share the knowledge and then we will move forward. So I think a fundamental change needs to happen in the global way we are doing material science. And I think we are providing the ideal platform to make that change happening.
We mentioned this standardization and reproducibility. How do you have any ideas for actually building a community where there is that collaboration instead of in parallel people just trying to make as much money as possible and profit as much as possible? How do you see that collaboration ensuing? And maybe how does VSParticle help in facilitating that type of collaborative future?
As I mentioned, if you want to collaborate, you need to have a technology that is reproducible. So if I make a sample in my lab and I want to collaborate with someone in Canada, he needs to be able to make the same sample and work on top of my initial research. And that is missing, and that's something that we first need to establish. But second is that there is a huge gap between the research ecosystem and the industrial ecosystem. So researchers are currently optimizing their work on publication in Nature and Science, which is, again, great for your scientific career, but not always the best for the future of humanity. And it's not always directly connected to the problems that industry is facing. On the other side, industry is optimizing for economic return, which is not always the best for society, but it's the best for the shareholder value. But in between those two ecosystems, there's a huge gap because it's very difficult to talk with each other. Industry is somewhat scared to really, let's say, explain their fundamental problems that they have. They don't want to give too much insights to the researchers because maybe they will then mention those insights to their competitor, which loses their competitive edge. You can imagine if you are a company with sufficient budgets that you can develop new materials, and you have developed this new material in the past 15 years and finally bringing it into the market, that you need to do everything you can to protect it. So it's not an open, it's not a collaborative ecosystem. And we think that VSParticle could be a very important role in between, because we are both enabling the industrial side. We are also enabling the research side. We also have ideas how to, in the future, accelerate material development from days to minutes. So we take a next step so that you could really introduce a new material every 12 months. And we just think that as the middleman, we could really bring them together, and then also maybe put some effort in defining roadmaps of applications that are really helping society, that are really helping us to decarbonize in the next 10 years and scale those applications towards 2050.
Wow. Yeah, I'm just trying to think. I know I put you on the spot, but that was a great answer.
No, but again, it's not something that we can all do by ourselves. So we are taking initial steps to build this community through our platform Material Pioneers. So we hosted 2 online summits in the past, fully focusing on accelerating the development of electrocatalysts. Again, they are playing an essential role in CO2 electrolysis and hydrogen electrolysis, but also in all kinds of battery type of applications and adjacent fields. So electrocatalyst is a very important aspect. There's still a lot to be discovered. There's a huge amount of new materials to be unlocked. So maybe to put it a bit in perspective, in the past, we have always used heterogeneous catalysis, which are solid materials that are activated through high pressures and high temperatures. And those high pressures and temperatures we are generating by burning coal or fossil fuels or some of the things that we don't want to do anymore. So we need to shift this whole, let's say, catalysis/chemistry industry, which is a huge part of our economy, to a process that is driven by electricity, basically electrons coming from windmills and solar panels. And that is the whole challenge of electrocatalysis. And it's really still somewhat in the infinite state. And there's so much more that we need to do to make those developments and get them to industrial scale in the next 10 years. That's an unprecedented challenge that the material development ecosystem faces. And that can only be developed from our perspective by creating this innovation highway, as we call it, by empowering the fundamental academia or ecosystem with standardization and a very fast process, and connecting them as close as possible to the industrial manufacturers to get those innovations into the industry.
Yeah, it's cool to see how you and Material Pioneers as a whole has emphasized the importance of that community aspect in addition to the technical advancement. And we're excited to, collaborate with Material Pioneers, be part of that community
definitely
as well. So yeah, I guess we discussed a wide range of, impacts that nanoprinting could have on the research scale and like the industrial scale as well. And so this new level of fast-paced innovation, I guess we would just love to hear your advice for MSCs who would like to pursue a career in this industry related to nanotechnology. Can you just share your final piece of advice for MSCs based on your experiences and what you've learned along the way?
First of all, I think you need to do some basic studies. So you need to go to university or do any of the nanobiology or chemical engineering, something that I did myself, or nanotechnology type of studies to get the basic insights in this field and to get a basic understanding of what it is able to do. But secondly, what I think is very interesting, especially that's something that is very active at the University of Delft, is they call them dream teams. So we see more and more student teams. So it's a collection of students that are taking off, I think, a year. And then together they are building solar cars, solar boats, hyperloops, fuel cell cars, whatever you can think of. The maybe in the coming years they will build quantum computers even. So anything that they can do within a year because of the enormous engineering power we have gained with all kinds of software computers and all kinds of engineering capabilities. And that is something that I really, really admire, because then you are really putting your knowledge in a very pragmatic way into practice in an ecosystem where it's okay to fail. And you better fail fast because you only have a year, and then you have some competition that you are participating in to compete with others. And I think next to just the basics, so understanding quantum computing or quantum mechanism, or understanding how new materials are developed, these very practical things are I think, a great value. And it gives you a bit of a taste of what is also happening when you build a company or when you're active in industry. And I really think that those students that take that year off and really learn those other skills are much more interesting for big customers or big companies, or also for small companies to get them in, because they know how to manage just projects that you need to manage yourself or get things done. And these things. I had sufficient time in the last 7 years to really understand more some of the macroscopic phenomena. And I think that is, if you want to apply your knowledge and your experience, if you did something like a dream team or some of these student competitions, and you want to take the next step in your career, so you finish your studies and you want to apply for a job, I think it's always valuable to know what is very important for I would say, the next decades of humanity, and make your selection on which, let's say, big problem you want to solve, and then look for companies that are active in that space, and then grow that space by becoming active yourself. So trying to be more orientated from your own personal interest, and you're willing to contribute to the progress of humanity, instead of only being focused on which job opening is open and where can I squeeze my CV in. Again, you always need to do a bit of both, because otherwise maybe it's difficult to find a job in that space, but try to stay as close as possible to where you want to contribute, instead of who is just willing to pay you for your work.
Right. Yeah. Play the long game, if you will. And I like I like the aspect of the dream teams and taking that full year off to just fail fast, and you continue to learn that way and really equip yourself. So I'm glad you mentioned that. And I'm very happy that you were able to join us today. I learned a lot, and I'm excited about VSParticle and excited to follow along with your journey. So thank you so much for joining. Yeah,
thanks again for having me. And I really enjoyed the conversation. Looking forward to all the comments that are coming afterwards. But thanks.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.